Okay, let's start. Today we are going to learn about American Fuzzy Loop, which is one of the most fundamental or most popular gray box fuzzer framework. And um, and in previous terms, actually, this is one of the most important topic because it was related to the project-based assignment in previous terms. But in this term, because we are kind of like, because this project is so famous that many large language models have used it for training. So students can easily do the project-based assignments if we are still using American Fuzzy Loop. So so it becomes less important. But it's still good for us to learn about the physics mechanisms of this, how this is designed and how it works, because it's a very it's a very practical framework, and and the designs are so classic that they were used in many research and publications as well. So here's today's outline. So let's have an overview first and then start to learn about different mechanisms of AFL. So here's the background. So the full name of AFL is American Fuzzy Loop. It is a gray box fuzzer developed by Mikhail, and when this guy was working for Google. And And if you wonder, like, what is AFL, it is actually the name of some kind of rabbits. So it's actually, if you wonder how does it look, it looks like this. So this is AFL. And maybe you have heard about this AFL as well, like Australian Football League, but the AFL is actually the rabbit here, not this one. And it is, and AFL is considered as this like the most classic gray box fuzzer, and it has been used for developing many different variants. And there are many academic fuzzers which are based on AFL. And if you wonder like who made this, so who made this tool, here are some more information about this, the author of AFL. So his name is like Mikhail some kind of ski, and he's actually a very famous white hat hacker. And talking about ski, it's not this kind of ski. It's actually you can tell that this guy has some like uh is this is like a very popular name in some like Eastern Europe countries, right? And this guy is actually from Poland. So so this was him, and he's one of the most influential white hat hacker, which means that he's hacking for ethical purposes. And this was him, and this is how he looks right now, and this is also him. I think this one is relatively new. So this is the author of AFL, and there are some, and AFL is actually uh, a project maintained by Google, because now this guy, the author, doesn't work for Google anymore. And it was archived by Google in 2024 because there is a better project right now, which is called AFL++. It was maintained not by any commercial companies. It's maintained by the community. And this is AFL++. And just like it's kind of similar to the relationship between like C and C++. Like AFL++ is like an extended version of AFL with many research features integrated as the default implementation. So AFL++ is considered like a better version of AFL. So that's why Google decided to archive the project of AFL. But we are still learning AFL instead of AFL++ here, because the key concepts are still the same between these two projects. And those key concepts are kind of important for for us to understand why gray box fuzzers can work effectively. So this is the background. And let's have an overview of the code repository of AFL. So if we look at the the directories, here are the top level folders from the code repo, and here are the files from the top level of the code repo. And the first directory is called dictionaries. It's actually the example dictionary for dictionary-based mutations. We will learn about this later today. And there are some experimental features, which some of them are already integrated as the default feature of AFL++. And this lab dislocator is something similar to a dry sanitizer, which is to harden the target project during compilation to make it more sensitive to report bugs. And there are some like lab tokenizer, which is to automatically generate dictionaries during compilation. So this is lab token cap. And there's LLVM mode, which is related to using the LLVM to instrument the target program. And we will learn about the different mechanisms of instrumentations later today. And there's also a premium mode, which is to use the quick calculator to instrument binary programs when they don't have source code. So that's the case. And the last folder is about because AFL is like a mutation-based gray box fuzzer. So talking about mutations, we need to have some seeds for us to mutate, right? So this test cases is actually the initial seed test inputs that could be used for mutation. So provided by the author of AFL. So that's all about the folders. And talking about the files, each file is actually an individual tool. So the first file is actually the utility to analyze the file format of the target program we are going to fuzz. The second one is the AFL's assembler, which is to add instrumentations to the assembly code of AFL. And this AFL-fuzz.c file is the main logic of the fuzzer. And it has over 8,000 lines of code inside this single file. So don't try this at home. So it's not a good practice to like put all the logic into just one file. But since this author is a very, like we have seen that he's a very famous hacker and he's a very smart guy. So he wrote this 8,000 lines of code just into one file without like any error. So this is the main logic of AFL. And AFL-GCC is the compiler's wrapper of GCC of the normal C compiler to add instrumentations. And AFL show map is to show the bitmap content like of particular seeds. So this is to show the coverage of any test inputs. And AFL Simian is a utility to minimize the initial seed corpus. So C here stands for corpus. So we will learn about this later as well. So this is an overview of the code repository of AFL. And here's the workflow of using AFL. So what we need to do is, because we are doing gray box fuzzing, so we need to collect information, like runtime information when we execute the target program. And what we need to do first is we need to instrument the target to inject some logic into the target program to collect runtime information. So there are different scenarios. If we have source code, we can compile with AFL's compiler wrappers. Like we can use the GCC wrapper, we can use the CLang wrapper. And without source code, we can use the simulators like Qimel to instrument the binary, or we can use some binary writers or even some hardware features to do this instrumentation. And there are some other preparations after we instrument the target. What we need to do is that first we need to prepare some good initial seeds as the initial test cases for us to create new test inputs automatically. And maybe sometimes we need to use AFL simeon to minimize the seed copiers. And sometimes if the target is full of some magic bytes, we may need to prepare some dictionaries to help to utilize the dictionary-based mutations. And sometimes we may need to study the target well to know that which features of the target we are going to test, right? And if we are running AFL for the first time, we need to set the CPU mode, which is to bind the father's process to a particular CPU. And then we can execute AFL. So after all the preparations and instrumentations of the target, then we can execute the target. And during the execution, what we need to do is we need to observe the key information to check if the father runs properly or not. Because sometimes if we don't do the preparations or instrumentations properly, the fuzzing process may run into problems. And during the fuzzing process, if we find any crash, what we need to do is we need to do crash triaging because many crashes could be due to one single bug. So we need to categorize the crashes into several different individual bugs. So that's crash triaging, and then we also need to debug the target, right? Because crash means like we found a bug. So this is the overall workflow of AFL. So you can see that most of the manual work are done before we start fuzzing, right? And after start fuzzing, we can automatically allow AFL to generate test cases and to report bugs for us. So we don't. So this is like because most of the heavy work is done automatically, so we can so it can save us some manual effort for finding bugs. And here is the user interface of AFL. So it looks like this. So you can see that it's like something like this is a terminal user interface. It's kind of like printed out in your terminal. So this one slave here is actually means that this instance of the fuzzing process is a slave process. We can run multiple instances in parallel. And we will learn about this later today. And here, this cycle means because for gray box fuzzer, we need to maintain a pool of seeds, like good test cases as seeds. So we are cycling through the seeds. So each cycle means that we have tried out all the seeds. And the stage progress is like the current mutation operator, some useful information about the current like mutation operator. Like for example, splice here means that we are trying to combine two seeds, parts of the two seeds together to make new test cases. And total executions means that the total number of test cases we have tested so far. And this is like the performance of each mutation operator. We can see that there are many different mutation operators here. And on the left-hand side, it means that how many new seeds are found by this mutation operator. And the right-hand side means that how many like test inputs have we created with the mutation operator. And the path here, you can see on the top right corner, this is the overall result. And path here means like it's it's different from the path we have learned for control flow graph. It is like one path is just one seed we kept. So for AFL, and crash is defined as like triggering the abnormal behaviors. Like for example, the program like is reporting some like sig is like emitting some like error signals. And map coverage is related to this part. This section here is related to the special type of code coverage used by FL. We will learn about how this coverage is calculated later. And this last part is like the stability is actually related to the randomness of the target program. So if we run the target twice and the coverage with the same input, the coverage could be different sometimes because sometimes the program have some randomness inside and they may execute different program paths according to the result of some random numbers. And in that case, stability will drop because we get different execution traces across different runs with the same test input. So that's the meaning of stability. So you can see that there are so many features of AFL just purely from this, even just from the user interface. So we are only going to learn some key mechanisms. So you don't need to worry about remembering all of them. And in this course, we're also not interested in like asking you to recite all these things, to remember all these things, but you need to just appreciate like why it works and what are the mechanisms behind. So if you wonder like how this user interface is created, like this one is like a very nice looking like terminal interface. And if you wonder like, okay, how is this one created? It's actually created purely by printf. And there's no external like terminal UI libraries used by the author. So it's purely by printf. And I'll show you the source code. Sorry, there are some problems with my earphone. And so this is the source code of how this is done. So the author actually defined some colors or some like utilities to draw the lines here for each section of the father's UI. And then he wrote this, like, Lord, forgive me about this. So he wrote a big chunk of code to print out the entire UI here. So it's entirely printed out by printf. And that's all about the overview of AFL. And let's learn about some key mechanisms of why AFL works and how it works. So the first part is about instrumentations. So we know that instrumentations are used to inject some logic into the target program. And the purpose of this instrumentation is to modify the behavior of the target program. Like, for example, we can use instrumentations to collect runtime information. And remember in our last lecture, we also mentioned about we can also try to use instrumentations to speed up the execution of the target program. And let's see how it is done today. So there are actually two types of instrumented code. The first is called fork server. And this fork server is a concept used for Linux or Unix like systems to control the process of the target program. And the communication between it is to allow the father process to control the target program's process. And we need some like inter-process communication mechanisms. And the inter-process communication is done with pipe of these Linux systems. And the second type of instrumented code is to collect coverage information. And this is, of course, it is used for collecting the information. And the IPC or inter-process communication channel used for collecting the coverage is to use shared memory. So there are actually many different like inter-process communication channels, like types like shared memory or some other like mechanisms, or even sometimes we can use a local HTTP server to do the communication. But here are the two types of IPC channels used by AFL. So, these pipe and shared memory are used for like doing the facilitating the communication between the father and the instrumented code. So just now we briefly covered like the different cases for doing instrumentation. So if we have source code, we can use like different compiler wrappers provided by AFL to do the instrumentation. So what we need to do is there are several these type of we can have several choices here. If we use this family of compiler wrappers, we are actually instrumenting hard-coded assembly code with this AFL AI's utility into the target program. So the injected code is actually hard-coded assembly code by the author of AFL. So if you click on this link, you can jump to the source code. You can see the author just hard code assembly code to inject into the, because like when we do compilation, we are like converting the program into assembly code first, and then we compile it as like machine code, right? So, so the instrumentation is done at assembly level. So the author just hand write these assembly code. So this is how it works. And because it's assembly code, so it actually depends on the CPU type. So you will need different assembly this AFL-AIS.h file for different target CPUs. So this is not a very good choice. And the better choice is to use AFL CLAN fast. So this one is to instrument with LLVM IR. So we know that if we, so CLAN is actually the compiler provided by the LLVM project. And this IR is actually the intermediate representation that is used during the compilation. So we know that, and so if you have taken the compiler like course, you will know that when we do compilation, it's not like we are directly translating the source code into machine code into the binaries. We are actually translating the source code into some kind of intermediate representation first, and so that we can apply some like optimizations or modifications, and then we gradually compile it as assembly code and then compile it as machine code, right? So this one here actually is that we can do the instrumentation at the IR level. So it's like more high level than the assembly code. So that we can enjoy the compiler optimization, right? Because compiler optimizations are applied at IR level. So, and it's easier for us to implement more complex logic, because you can see we have just seen that writing assembly code is like much harder than writing the IR code. However, it requires, the drawback is that we need to install the whole like environment for LLVM, which is sometimes very tedious. But most of the time, if we have source code, we prefer to use the LLVM-based instrumentations. And sometimes we can also instrument the target without source code. So if we don't have source code, we can use the AFL Quimio utility. Quimio is like it's a shortcut for quick emulator. And this project is used like creating like a virtual machine for like for Linux systems. So They also provide an IR for running programs in the virtual machine. So we can do instrumentations using the criminal IR without source code. And if you are familiar with virtual machines, you know that they can run in user mode or system mode. So if the host operating system is the same as the target system running inside the virtual machine, then we can run the programs in user mode. Otherwise, we have to run full system emulation. So this is like the difference between these two modes. And this utility is already provided by AFL in its own repository. And apart from using emulators, we can also try to use some binary rewriters. So there are several like binary rewriting frameworks, and we can try to use them to like modify the program binary directly to inject logic inside. So it's generally considered to be faster than doing emulation on virtual machines because we don't need to have the overhead of running the virtual machine, right? We just need to directly modify the binary and run it. But you can imagine that it's very fragile because binaries are like very compact format, and so sometimes it's not very stable if you just use these binary writers. And for some special CPUs, we can also try to use the CPU support to do instrumentation or to collect runtime information. So for example, for Intel CPUs, there are some utilities called Intel PT, which can help us to collect the branches inside the program. So we can use those utilities of the hardware to capture the coverage information. But CPU support doesn't, because it's limited by the capability provided by the hardware. So we cannot do very complex, we cannot inject complex logic into the target program. So we can inject fork server into the target program if we use CPU mode. Like for example, for Intel, we have PT, for ARM, we have Corset. And that's all about the overview of the instrumentations. And now let's learn about the first type, instrumented code by AFL. So the first type is fork server. So before we jump into the details of fork server, let's think about the key function here, fork. Fork is a system call used by all the Linux system or like Linux, some similar systems like maybe the Mac OS or Android OS because Android has a Linux kernel inside. So it is the system call that is used to create a process by duplicating the calling process. So the new process is like fork is like similar to how we fork a Git repository, right? It's like creating a diverging branch. Like for processes, it's like creating a new process out of the parent process. So the original process is known as the parent process, and the newly created process is known as the child process. And it has an important feature of copy on write, which means that the child will not create or will not get allocated new memory regions unless it's trying to write into the memory. So if the child process is reading from the memory, it will not require the system to allocate new memory regions. This means that the child can share the memory with the parent if it's only reading from the memory, right? So this can save us some time and memory when we create new process. So this copy on write is like saving both time and memory space. And this is a very simple example of how fork works. And you can also try this. You can try this out in a website called this one compiler. So this website is actually very, very useful for you to try out some example code. And it actually supports many different programming languages. And it's running like it has a web interface, but the mechanism of this website is very different from um, the 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 uh, the the tools we used for our assignments. This one it does have a backend, but for our assignments we don't have backends. So for this one here, you can see that. So the return value of the fork function is just a child PID. So this child PID works for two purposes. So first, it works as a status code. So if this child PID is smaller than 0, then it means that the fork function has failed. So this is the first purpose. And the second purpose of this is to distinguish between child process and parent process. So if the value of child process PID is 0, then it means that the logic of this code block is running inside the child process. And if the value of child PID is larger than 0, then this chunk of code is running inside the parent process. So we can use the value of child PID to determine like which process is running what kind of code. So this is how it works. So we can see if we run this, you can see that this one is printed out from the child process, and this one is printed out from the parent process. So this is how it works. So it's basically like forking one process out of the parent process. So because of the characteristic of copy and write, we can, if we use this fork function to create processes, it's very fast and it can actually save as actual memory usage. And if you are interested in more information like how fork works, you can go to the Linux manual page to have a look. And the second key system call mm, we need to learn is like the pipe. So pipe is used for doing the inter-process communication here. So pipe is and FIFOs are like first in first out are like providing some like unidirectional inter-process communication channel between different processes in the system. So a pipe has a read end and a write end. So it's like we are on one side of the pipe, we can only read. On the other side of the same pipe, we can only write. So this is the characteristic, and so that's the characteristic of pipe. So you can consider it like this. So it's like it has a direction here, and AFL actually uses two different types, and types are known are implemented as file descriptors here. So file descriptors is like a special mechanism of the POSIX uh, operating systems, and you don't need to. If you are interested in like the details of file descriptors, you can click on this link, and it will direct you to the wiki page and you can get more information. But for now, we just need to know that these are just like the IDs given to the pipes. So for each pipe, we do have like one end for writing some information into the pipe, and on the other end of the pipe, we can only read. So there are two pipes here used by AFL. So the first one is Fox Server FD, which is written by AFL and read by the target. And there's another pipe called whose ID is just FD plus one. It's written by the target and read by AFL. So we can do two-way communication using these two types. And if you are interested in what is the mechanism of pipe, you can refer to the menu page of Linux. And here's the source code of a Fox server if you are interested. So there are some logics into the instrumented code, and there are some like code in the AFL files to like handle the communication with the instrumented code. So these are the the different locations inside the source code files. And we will learn about how this Fox server works, like how does AFL control the execution of the target program in the next slide. So remember, we have two pipes here to do two-way communication. And for with these two pipes here, so one is the pink one and the other one is the blue one. So what we do is when we run AFL, it actually forks into two processes. The first one is the parent process is actually AFL, the father's main process. It will be used as a father's main process. And for the child process, it will invoke execve to, to, to invoke the target program's process. And the target program, because we have injected a Fox server logic into the target program, so the target program will start at the state of being a Fox server here. And once we have started these two processes, this is what we will do. So the Fox server process will wait for the pipe to receive information. So it will wait for the signal from the father side. And for the father, it will write to the pipe telling the target process that, okay, it is ready. You are ready to create a new target, to fork a new target process for me to test with. And then it will wait for the feedback from the target process. So it will use the pink colored pipe to write to the target to tell it, okay, you are ready. So I'm ready to test a new process. So please like just create a new target process for us to do testing. So it will, once the target Fox server receives the signal from AFL, it will fork a new process. And this new process is the actual process that executes the test input. So do you know why we need to create like this green colored process to run the test inputs rather than just using like the yellow one to run it? The purpose is that because sometimes we are trying to find crashes, right? So sometimes the target process may just crash. So if this yellow colored like process just crashes, then there's no Fox server anymore, right? We need to start the process again, right, from scratch. So we need to have this Fox server. We need to keep it running and just spawn new processes to do testing. So this is why. And after this new process is created, we just tell AFL about the PID of the executor and then wait for the executor to finish. So it tells AFL the process ID of the target process with the blue colored pipe, and AFL receives this and will start to wait again. And in the meanwhile, this green color process is like running, right? After it finishes, it will generate an exit signal. And this exit signal can tell us whether this process exit normally or abnormally. So if the exit signal is like some signals like a SIG segment fault, then we know that there are some bugs, right? So then the Fox server process will tell the signal to AFL because AFL is like the father is waiting here right now. So this one, so the Fox server will tell AFL about the result of the signal, and the AFL will handle the result accordingly. So if the signal is like a crash, then the AFL will report. Remember, there was a UI on the AFL, right, telling how many crashes we have found. So AFL will report that, okay, there's a crash. And so it will handle the execution results afterwards. And then it will generate a new test input. And after generating the new test input, it will write to the pipe again and wait for the feedback again. So this write is actually the same as this one here. So this marks a whole loop of whole round of communications between like AFL and the Fox server process. So this is the workflow of Fox server. The Fox server is actually a mechanism that can help to speed up the execution because when we create the target, every time you can see that every time we do a round of like we create a new test input, we need to create a new like green colored process, right? And this green colored process is actually forked from the target programs, like a long running process. So it's not like starting a new process from scratch. It's not like starting a new process from scratch. So it can help us to skip the environment setup for the process. So we can save time to speed up the execution of the target program. So this is how it works. And the second type of instrumentation is to collect coverage feedback. And remember, the IPC channel used for collecting coverage feedback is shared memory rather than pipe here. So the POSIX systems allow different processes to share a region of memory. So a region of memory, you can consider it as an array of bytes, right? An array of bytes. So two processes can both read and write from a piece of shared memory. And by default, AFL uses a piece of shared memory like this large to collect and store the coverage information of the target. And this is how it works. So the target program will write to the shared memory each time it finds a new edge. It covers a new edge. And AFL will only read from the shared memory. And the shared memory is also known as bitmap in AFL. So if you want to know more about how shared memory works, you can refer to this menu page. So now let's think about what is written to the shared memory. So we know that we need to collect coverage from the target instrument program, right? And this is like the source code of the instrumented logic to emit the coverage information to the shared memory. And you don't need to learn about the details of this source code, but we need to know that for every how it works. So for every basic block of the control flow graph, we assign an ID to that basic block. And then we do some calculation and write something to the shared memory during the execution of that basic block. And so you may wonder, okay, what's written to the shared memory, right? This is what's being written to the shared memory. So it's written as, so we use so shared memory is like an array of bytes, and array has indexes, right? So we need to first locate the index first about where we are going, when we write to an array, right? So we use the ID of previous basic block doing a write shift by 1 bit, XOR the ID of the current basic block as the index for writing to the shared memory, like the byte array of bytes. So this is the index. And once we have located the index for writing this into this array, we need to think about the actual content written into the array of bytes, right? So it's very simple. We just so once we have determined the ID, we just +1 for that uh, for the byte in that index. So you can see that because we are not using the IDs of the basic blocks as the index for writing into the bitmap, so we are actually not collecting like coverage of basic blocks. We are collecting coverage of basic block transitions. So for each basic block, because we are using both the previous basic block's ID and the current basic block's ID to calculate the index. So this index is actually capturing the transitions between basic blocks. So AFL actually collects basic block transitions rather than like real path coverage or basic block coverage. So it's like transition coverage. And because the content we stored is like +1 every time we reach an ID, right? We cover a transition, right? So the actual content of the bitmap is how many times we have executed the basic block transition with the ID of that part. So this is the overall workflow of how this shared memory works. So once we have executed the target program, it's actually writing into the basic blocks. And if a transition between two basic blocks is covered, then this value will change. The value in that ID corresponding to that ID will change. And the FL will just read from the bitmap to collect the coverage information. So this is how it works. And you may wonder, okay, so we are using the previous ID of previous basic block right shift by 1 bit, XOR the ID of the current basic block as the unique ID for basic block transitions. So why don't we just use like ID XOR ID without the shift? So why do we need this right shifting here? So you have two choices. We can use this right shift to handle like cases where like maybe a branch is connecting to multiple basic blocks, or we use this to handle the cases where like a basic block is looping back to itself. So we know that this XOR kind of thing is like helping us to generate some unique IDs for edges between basic blocks. So why do we need to do the shifting here? Why do we need to shift? Let's see the results. Okay, half. So the correct answer is the second one. It's answer B. So let's see why. So if we don't do so we know that each basic block is assigned with some sort of ID, right? And if we don't do the right shift, it's basically the ID of because we are using the ID of the previously executed basic block XOR the ID of the current basic block. If we do a self loop, both the previous ID and the current ID are the same ID here, right? Are the same here because we are doing a self loop. So the previous ID is the same as the current ID. So it will always be 0. So the index will always be 0. imagine there could be many different locations for like self-looping inside a big program, right? So all of them will share the same like zero index. Then they are writing to the same byte inside the byte array, like the bitmap, right? So in this case, we cannot differentiate between like multiple different instances of self-looping basic blocks. So that's why we cannot directly like doing the XOR without doing the right shifting. However, if we do the right shift, so this time the previous ID is, if we do a self-looping here, the previous ID will be different from the current ID, right? And then if we do XOR, we will get a different number. And this will make sure that it won't always point to zero, right? Because something XOR itself will always give us zero. So if we don't do the right shifting, all the self-looping basic blocks will just point to the same locations. So the correct answer is answer B, because we need to handle this self-looping issue. Okay, so that's all about instrumentation, and let's have maybe 5 minutes break, and I'll see you at 1/4. Okay, let's continue. So today's content is like could be very hard if you try to just master the like mechanisms of AFL, but you don't need to be a master of like uh the gray box fuzzing. You just need to know how it works, like the mechanism, understand the mechanism, and that's all. So for your assignment. 3, question 5, you will be practicing like uh, seed handling and seed mutation. So if you so if you um so if you understand like how it works, it will help you to like uh, actually do your assignment 3 questions. And but you don't need to fully master like every detail here to do the assignment questions. So that's a basic idea here. And there are many like details and considerations when the author of AFL writes the code. So there are some very like smart designs inside, but we don't need to learn all of them. We just need to learn the most basic ones. Okay, so let's continue to seed handling. So the first thing we need to think about for seed handling is we need to store new seeds, right? We need to store some interesting test inputs as the seed for creating more test inputs. So this is the purpose. So in our last lecture, we have learned about that this is the key mechanism of gray box fuzzing, right? If you can if we'd like to do some divide and conquer style of program state exploration, we need to store new seeds. And remember, the key capability of the smart gray box fuzzer we learned in the last lecture is to have awareness of coverage and to be able to keep new seeds that can give us more coverage, right? So just now the instrumentation is used for handling to bring awareness of coverage. And now let's think about the decision of keeping new seeds. So these are the two key things. And branches are roughly, so we in the previous lecture we used the term branch coverage. And actually branches are roughly basic block transitions, right? So most of the time, like whenever there's an edge, there is like some kind of branches between basic blocks. So we can roughly think of branches the same as basic block transitions. And AFL stores, the key decision is very simple. AFL just store a test input as a new seed. If it can cover at least one new branch or new basic block transition that hasn't been seen before. So that's it. Or sometimes like, but there are some special cases. So if it can increase the loop count of that particular like transition. But this is a little bit complex here, so we just care about the behavior of the new branch for now. And it has a very smart design. Each byte has 256 possibilities. So it's impossible to store just like 256 seeds per branch. So AFL has a very smart design to store the loop counts according to different bins. So if you're interested, you can learn about this mechanism from the source code. But we won't go through the details about this one here. We just need to know that whenever there's a new branch covered by brought by the particular test input, we keep it as a seed. So this is roughly how it works. And this is like the overall mechanism of how it works. So AFL just maintain a global bitmap, which is the coverage of all the seeds we have encountered. So remember, each byte of the bitmap represents a unique transition, right? So if a unique transition, the value of that byte in the bitmap is not 0, then it means that the transition represented by that byte has been covered. So AFL uses this to keep track of the global coverage it has encountered. And whenever it gets a new coverage from the seed, from the text input, it receives a bitmap, right? It will compare the seed bitmap with the global bitmap and see if the seed bitmap can cover some new bytes that is like not covered in the global bitmap. And if the seed bitmap can bring in more than one byte that is not marked as non-zero by the global bitmap, it will be marked as interesting and will be kept in the seed queue. So this is how it works. So at least if this seed can bring in at least more edges, then it will be kept. So that's the key idea here. And this is very related to your assignment 3. And here is a closer look at the information display of this coverage on the terminal UI of AFL. So it has a unique section of to display the coverage. See here, you can see the map coverage here. So remember, this total path is actually the total number of seeds we have kept, and the left-hand side is like the number of branches covered by the current seed divided. So it's like divided by the bitmap size. So this is the left-hand side percentage, the meaning of this. And on the right-hand side is actually the number of branches covered by the global bitmap, which is like the coverage of all the seeds, of all the test cases we have encountered now. So because remember, the AFL is maintaining a global coverage state, right? So this is the global one. This is the current one. And this count coverage is like the average loop count for each branch. And we don't need to care about this loop counting here. We just need to know that AFL is maintaining like a bitmap for each seed, and it also has a global bitmap to check if a particular seed can bring in new coverage or not. So this is a detailed explanation of this coverage information of the terminal UI. And now let's think about another strategy for dealing with seed we have covered in our yesterday's lecture is seed prioritization. So seed prioritization is to determine, because we have a queue or a pool of seeds, so we have to think about which seed should we use next, right? AFL has so this is the definition of seed prioritization. And AFL is actually maintaining a priority queue by marking some seeds as favored. So it will use the favored seeds first. And if there are no favored seeds, then it will use the normal seeds. So it's kind of like the concept of priority seating in the public transportations. So this is roughly how it works. So in one cycle, it will go through all the seeds one by one. And when going through the seeds one by one, the AFL will check if there are unused favored seeds yet. If there are unused favored seeds in the queue, it will be very likely to skip the current one if it is not favored. And that's roughly how it works. And if you wonder how the favored seeds are calculated, it's like this. So remember, we would like to prioritize seeds with better quality, right? And the way we need to somehow determine the quality of the seed. And here AFL uses maintains a dictionary. And this dictionary is something like a Python dictionary or like a hash table here. So the keys of the dictionary are the basic block transitions or the edges covered by all current seeds. So remember there's a global bitmap, right? When AFL knows all the edges, all the index of the edges we have already covered by all the seeds. And the value of the key is a list of seeds that can cover that edge. Then AFL will sort because there's like one list per edge. AFL will sort all the lists according to this. So according to the value of execution time times the file size of the seed from small to large. So this is a score received by each seed. So we have to calculate the quality of the seed, and this is how we calculate the quality here. So you just use execution time of the seed times the file size of the seed. And then for every seed at the first of each list, it is collected, it's marked as favored. So this is how it works. So based on this mechanism, the setup, this is a very smart design. So the set of the favored seed, because we are selecting one seed, one favored seed per list, and each list is associated with an edge that we can cover, right? So we are actually making sure that the favored seed can cover all the edges we have already seen, right? It's actually a, it's actually a set of seed that can cover all coverage we already have. And the seeds are like both small and fast executing. And we can see why this works in the next slide. And actually the AFL corpus minimization purpose, the like utility actually use the same mechanism to calculate the favored seed. Let's see how it works. So let's assume that we have 4 edges and we have 3 seeds. So seed A can cover edge 1, edge 2, and edge 4. And the score of seed A is like the execution time times the size of seed A, so which is 20. And for seed B, let's assume that it can cover edge 1, edge 2, edge 3, and the score is 150. And for seed C, the let's assume that it can cover edge 3 and edge 4, and the score is also 20. So the score is like the smaller the better here, right? Because we want the seeds to be as small as possible, and we want them to be executing as fast as possible. Then we can build this dictionary or the hash table. So the key of this hash table are the edges we have already encountered. So we can see that we have 4 keys, right? Because we have covered 4 different edges. So for each key here, we can maintain a list. So this list is like the list of seeds that can cover this edge. So for example, for edge 1, we should include seed A and seed B into the list, right? We shouldn't include seed C because seed C cannot cover edge 1. So we should have seed A and seed B. And it is the same for all the rest of the edges. So we can build this list. And then we can sort the list and collect only the first item of the list. So based on what we have learned, can you quickly tell what is the final set of favored seeds according to this current dictionary of the edges and seeds? So the set is actually seed A and seed C, right? Seed B is not favored. And with the favored set of seeds, we can still cover all the edges, right? So seed A and seed C are enough to cover all the edges we have already encountered, right? Because we are selecting them according to this dictionary here. So this is a very smart design. So we can minimize the set of the set of seeds, and we can still make sure that we can cover all the edges with the minimal set of seeds. So this is how it works. And we're talking about the strategies used for seeds. Another strategy is power scheduling we have learned yesterday. So power scheduling is to decide once we have selected, okay, we are going to create new test inputs with a particular seed. The next decision we need to make is how many new test inputs should we create with the current seed, right? So this is about power scheduling. And the AFL actually calculates a performance score for each seed. And it's mainly based on the execution time and coverage. So actually there are more like design details, like many like good designs, but we just need to know that it's mainly determined by execution time and coverage. And you can see this is the actual like implementation of the power schedules. And if you're interested, you can find the details from this location of the file. So you can this is actually the line number of this file. So that's about seed prioritization and power scheduling. And now let's move on to seed mutation. So seed mutation is important for us to like create new test cases. And there are several strategies used by AFL. And basically they could be categorized into four main types. So the first one is trim, to reduce the size of the seed. So just now we learned that, okay, for the calculating the score, the smaller the better, right, the seed. But we don't know why it is like that case, the smaller the better. And let's see why when we learn trimming. And there are some deterministic mutation operators, and there are some non-deterministic mutation operators, and there are some dictionary-based mutation operators. So these concepts may overlap because trim is considered as a deterministic mutation, and dictionaries could be both deterministic and non-deterministic. So let's first talk about trim. So AFL, we just not learned that AFL favors smaller seeds, right? But why? Because the first one is the smaller seeds are faster to be processed by both AFL and the target. Because most of the time, if we give the target program a smaller file to process, it can execute faster, right? Generally. And because AFL needs to mutate needs to handle the seed files in its memory or inside the program. So if the files are smaller, then it takes less time for AFL to process, right? So it's faster for both the target and the father. And it's more compact. So which means that it's because if we can reach the same coverage with a larger file and a smaller file, we should always prefer the smaller file because if we do random mutation, it's more likely that we can hit some critical regions. We can mutate some critical regions inside the smaller file, right? For example, this is the format of a PDF file. So let's assume that we use this PDF file to test a PDF parser. So not all the content of the PDF file can affect the behavior of the parser, right? Because some of the content inside the file are just like text contents, which doesn't affect the parsing process of this file, right? So if we just if we just mutate, if we can get rid of those file content that doesn't affect the behavior of the target program, then if we do random mutation, we are more likely to hit the key bytes in the file that may affect the decision of the target program, right? So this is why we will like to do trimming. And here is how AFL works. So AFL will try to trim every seed by removing the bytes inside the file that doesn't affect the branch coverage. So if we remove, let's say if we remove a byte inside the seed and the coverage of the seed doesn't change, then it means that it's safe to remove that byte from the seed, right? So we can make the files smaller. And this is like very useful in practice, but if you try AFL with some toy targets, which may not react to the file size changes, you may encounter some confusions. And for deterministic mutation, it's called deterministic because if we apply the same set of mutation operators on the same target seed, we will always generate the same set of test inputs. So that's why it's called deterministic. So fixed set of test case means fixed count and fixed content. So we can see that on this UI, there are several types of fixed mutation operators like here. So for example, for bit flip, which means that we are flipping like 1, 2, or 4 consecutive bits from 0 to 1 or 1 to 0. So because we are flipping bit by bit, right? Every time we do a flip, we create a new test input. Every time we do a flip, we create a new test input. So if we apply this bit flipping on the same particular seed, no matter like how we run it, we will always get the same set of test inputs, right? If we do bit flipping. And it's the same for byte flips. So it's just like instead of flipping bit by bit, we can flip several bytes. And arithmetic is like plus or minus some like predefined numbers. And known integers is like to replace the short like different sizes of numbers with some special values. And these special values could be like some interesting values like the minimum or maximum possible value of each integer type here, or like some special values like 0, +1, 1 or -1, right? These are the special values. And that's about deterministic mutations. And there are some non-deterministic mutation operators as well, and is kind of known as random mutation. So for example, havoc means like we can, because for deterministic, we just apply one mutation to the seed. We don't apply multiple ones. So that's why it's deterministic. And for havoc mode, it means that we are randomly selecting multiple mutation operators, and we are randomly selecting multiple locations in the seed to apply the mutation operators. So this will, because every time we run, because there are some random selections here, right? So every time we run the mutation operator, we can get a different result. So that's why it's known as non-deterministic mutations. So havoc is one here. And we also have splice, which means that select we randomly select another seed in the seed pool and randomly cut the two seeds into four halves, and we randomly combine them together to build new seeds. So that's the splice mutation. And there are some dictionary-based mutation operators as well. So because we know that for programs there are some magic bytes, right? And it's very hard for us to randomly guess the values of those magic values. So what we can do is we can extract those magic values and use them to replace to put them into the test inputs we generate, right? So there are two ways of using this dictionary. So one is to use the dictionaries like deterministically, which means that we can replace the chunks or in place or insert the dictionary keys, dictionary values like token by token. So this is deterministic usage. And of course, we can also use it for as one of the selectable mutation operators for havoc or random mutations. And if you wonder how this dictionary is actually implemented, actually it's in under this folder here. And you can see that for different file types, we have different dictionaries. And dictionaries are just like some special values for that file type. For example, for this one is JS.diff. You can see these are the special values used by JavaScript. And this is like this is an example from the JPEG image. And the dictionary values are just like, because you can see the /x, right? It means it's a hexadecimal value here. So they are just some special file headers used in the JPEG images. So we can, when we do mutations, instead of randomly changing the content of the file, we can use this predefined content. So that's the idea of dictionaries. So it can help us to avoid guessing the correct content of the file. So this is dictionary-based mutation. And there are several tips when we choose different mutation strategies. So the first one is we should always use the dictionary whenever possible. So, but for this assignment, we don't have the chance to practice dictionary. But when you do real world fuzzing, you should always try dictionary. And most of the time, deterministic mutations may not be as good as the non-deterministic ones at most of the time, because the mutations are sometimes too subtle. For example, if we just do a bit flip, like it's like we are only flipping like one bit of from 0 to 1, 1 to 0. A file could be like a few hundred bytes, right? And that's like almost a few thousand of bits. So if we just flip one bit, then the change is too small to change the behavior of the target program. If we try out all the small mutations created by the deterministic mutation operators, then we are kind of like wasting time. So in order to disable basic mutation operators, you can use the -d command option for AFL, and you can use the -z for AFL++. So that's all about seed mutation. And now let's think about parallel fuzzing. So in practice, parallel fuzzing is to improve the effectiveness by or efficiency by applying multiple fuzzers to allow them to collaborate, to run together on a particular target. So this is parallel fuzzing. So we can run multiple instances to allow them to work together to maximize the hardware usage. So you can see this from this UI. We can see this CPU 002, like 139%, right? So this thing is like, because each instance, each process of AFL fuzzer is actually binded. There are some mechanism of binding some process to a particular CPU core. So each instance here is actually binded to a CPU core by default. So that CPU core is fully allocated to serve this process. So this can help us to speed up the execution of both the fuzzer and the target program. So this is like what you see here. And if you wonder how can we bind a process, to a CPU core, and this is the location of how it was implemented by AFL. But this only works for Linux systems. For Windows, you have to use some different mechanisms. And normally we can, for parallel funding, what we should do is we should run one master instance and multiple slave instances. So the master instance you can use deterministic and non-deterministic mutation operators, but for slave instances, they should only use the non-deterministic mutation operators. And the reason is that because because we only have one master instance and multiple slave instances, right? So if we allow slave instances to run deterministic mutation operators as well, then it's kind of like a waste of time, right? Because every time they use deterministic mutation operator, they will get the same set of test inputs generated. So there's no point of like running multiple instances with the same set of test inputs created, right? So that's why we shouldn't use slave instances to write to use deterministic mutation operators. So this is why, and if you wonder, okay, how do they collaborate? If we just run them in parallel without allowing them to like collaborate, then it makes then we are not fully utilizing them, right? Because they are like each further instance is like working on themselves. They are not collaborating. So the way to allow them to collaborate is that they share the findings, they share the seeds they have discovered by crawling the seed queue from other instances. So if you see here, this this imported value here is actually the number of seeds crawled from other instances running in parallel. So this is how they collaborate. So in practice, we should because nowadays all the CPUs are multi-core CPUs, we should try to do parallel fuzzing if you really want to find bugs. And that's all for today's content. And before we end, let's have a quick review of what we just learned. And AFL is actually a very good framework. And there are many detailed designs and many good design choices inside. And it's also a very practical tool if you would really like to find bugs or vulnerabilities in some real world projects. And if you are interested in this, you can use today's slide because there are a lot of links. There are a lot of links to external materials and resources. If you are interested, you should really look into them and try to play with AFL yourself and see if you can find any bugs in some real world projects. But if you're not interested, you should still learn about the key concepts and mechanisms of AFL because it's a very typical green box fuzzer. So the designs of AFL can inspire us to understand like the basic mechanisms of general gray box fuzzing. So that's what the purpose or the learning outcomes for today's lecture. So for today's lecture, we started with the overview of AFL. The overview of AFL it was created by like a very famous hacker, and this guy has and when logic is written in like 8,000 lines of C code, and the key mechanism of AFL is like we need to do is the key working flow is like we need to do instrumentation first, and then we prepare the seeds. We learn about the target, and then we can start fuzzing right with the instrumented target. And then during fuzzing, we need to observe for crashes. And if there are any crashes, we need to do crash triaging and also do some debugging, right? So this is like the basic usage of AFL. And since we have to do instrumentation, we can do instrumentations on different levels. If we have source code, we can use the wrappers of compilers provided by AFL to do the instrumentation, right? And when we do instrumentation, we can also try to instrument at the assembly code level or the IR level during compilation, right? And for and if we don't have source code, we can instrument the binary programs. We can use like virtual machines to do the instrumentation. We can use binary rewriters to do the instrumentation. We can also try to use the utilities provided by the CPUs to do instrumentation. And there are two types of instrumentations. The first one is Fox server. Fox server is used for like speeding up the execution speed of the target program, right? Because fork can help us to skip the environment setup for the new process. So if you can skip that overhead of setting up the environment for the new process, then we can execute the new process faster, right? So that's the key idea here of the fork server. And we learned about the very complex protocol of handshaking and communication between AFL and the Fox server, right? But you don't need to learn that in detail. You just need to know that, okay, roughly how it works. And for the other type of instrumentation is to use for collecting coverage, right? So we are assigning an ID for each basic block with a coverage instrumentation, and we use the XOR value of the previous ID redshift by 1 bit and the current basic block's ID as the index of the edge, right? And then we use this index to mark the bitmaps. And this bitmap, and the AFL has two bitmaps. The first one is the global bitmap, which is used to store the edge coverage of all the test inputs we have encountered. And for each new test input, we also have an individual bitmap. So for that, for the AFL gets the individual bitmap, it will try to compare this individual bitmap with the global bitmap to see if a particular seed can bring in new edge coverage. If new edge coverage can be brought, then AFL will just store the seed, right? And storing the seed is actually the first strategy we need to think about, seed handling. And there are two other strategies for seed handling. First one is seed prioritization. And AFL uses a priority queue by calculating the favored seeds. And you remember the favored seeds are calculated with some sort of dictionary, right? And this dictionary, for this dictionary, each key is an edge, and each value of the key associated with the key is a list of seeds that can cover that edge. And this favored set of seeds is actually the minimal set of seeds that can cover all the edges we have already encountered, right? It's like a representative set of seeds, so the favored seed. And the second, and another seed handling strategy is about power scheduling. So AFL will just assign some performance scores, and this performance score is mainly related to execution time and coverage of that seed. And for seed mutation, we have many different types of, and four different types of mutation operators. The first one is trim, so which is to reduce the size of the seeds we have already had in our seed pool. And the second type of mutation operator is the deterministic mutation operators. So we can do some bit flips, byte flips, we can do arithmetic or interesting value replacements, right? And for non-deterministic, it's basically just randomly selecting some mutation operators and apply them to some random locations in the seed. And for a dictionary-based mutation, it's like because for some file formats, there are some magic bytes, right? Instead of like randomly guessing those magic numbers or magic bytes, we just provide them to the fuzzer, so the fuzzer can just directly use them to modify the content of the files. So that's about dictionary-based mutations. And lastly, for practical usage of fuzzers, as each because we want the fuzzers to execute as fast as possible, so we are kind of like binding them to different CPU cores. And because modern CPUs have many different almost all of them are multi-core CPUs, right? So we can use different cores to run different instances of the fuzzer, and they can collaborate with each other by like sharing the seeds they have discovered. And also, when we do parallel fuzzing, we should only allow one instance to run deterministic mutations, and all the other instances should not run deterministic mutations. So yeah, so that's pretty much of it for today's lecture, and thank you for coming. Have a nice weekend.